So today we're going to learn about why DP is important and why we have to learn it. So this is important to understand why we learn something before we even start learning it, so we have the motivation to. So what is DP? It's just an abbreviation for dynamic programming. So dynamic programming is also called DP. So dynamic programming is basically a fast way of calculating the answer for a large range of different problems. So these range from the Fibonacci sequence to problems like, say, I have 2 ovens and I can use 2 ovens at the same time to cook. And given the time it takes to cook each meal, A1 to AN, how much time does it take? What's the least time it takes to cook all N meals? So there are a lot of problems that fit into the category of dynamic programming, and this is why it's probably regarded as a really difficult topic in programming in general, no matter what language. So today we're going to understand why we're trying to learn dynamic programming, so we have the motivation to continue in our future lessons. So let's start with the Fibonacci sequence. So I have the Fibonacci sequence. We all know that the Fibonacci sequence is 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. So there's an infinite number of Fibonacci terms, but these are the first couple of terms that we should know. So basically, the problem here is if I gave you, my input was my input is N, and I want my output to be Fn. So what's Fn? Fn is the nth term of the Fibonacci sequence. So now we're going to try to define our function Fn, right? So using what we know about recursive sequences, this is how we're going to do it. So I'm going to write this in C++, but it's really easy to convert into any other language. So we have this function here, the integer function, and the input is n, as we discussed. So basically, the first thing we do is, if n is less than or equal to 2, then we return 1. So why is this? We know that the first 2 terms of the Fibonacci sequence are 1 and 1, right? So if n is less than or equal to 2, we're basically returning the first or either the first or the second term of the Fibonacci sequence. So we just return 1. No more calculation can be done. And then in most cases, we don't have n is less than or equal to 2, so we return Fn minus 1 plus Fn minus 2. So this basically tells us that we return the sum of the Fibonacci, the n minus 1th Fibonacci number and the n minus 2nd Fibonacci number. And the sum of this is Fn. So we just keep doing this, and this is just our function. So now, if we try to draw our function out, so what I mean by draw is we graph a tree diagram for this recursive function here. Then we start with, we have, let's say the input n is 9. So we have n equals 9, and then for n equals 9, we split this up into n equals 8 and n equals 7. And we put the function into these again. So we split n equals 8 up into n equals 7 and also n equals 6. Then we also split the function n equals 7 up into n equals 6 and n equals 5. So once again, we split the n equals 7 up into n equals 6 and n equals 5. We split the function 6 up into n equals 5 and n equals 4. So we do the same thing here for the function 6. We split it up into n equals 5 and n equals 4. We also split this up into n equals 4. So let me just erase that. We split this up into n equals 4 and also n equals 3. So we just keep doing this until one time we have n equals 2 or n equals 1. So for example, here we have n equals 2 or n equals 1. So we just return 1, and we know that f3 is 1 plus 1, which is 2. So basically, this tree just goes on until every single branch here, the leaf of the branch here is 2 or 1. And then we start returning 1s, and we sum up the 1s to get the 3, to get f3, and then we sum up f3 and f4 to get f5, etc., until we get back to f9. So this function here, it works quite well, and it's really accurate for the first couple of terms for the Fibonacci sequence. However, if I input a large number, like a slightly larger number, let's say n equals 50 or n equals 100, then basically what will occur is that this function will continue running for a long time, and it might even give a huge output that doesn't even match the original one, the one that we were hoping to look for. So why is this? So from this tree here, we see that every time we have one n, we split it up into 2 n's. However, there are certain values here that are the same tree branch. So for example, we have the 7, 6, 5, 4, 3, 2, 1 here, and this is essentially the same branch as this one that I'm boxing. So these two are actually the same branches. But the problem here is we calculated them twice because we calculated them separately. And also we know that we have that the branch here, the F6, F5 plus F4 branch, is the same as this branch, and it's also the same as this branch here. So we're actually repetitively calculating a lot of things. For example, the F5s here are actually all the same too. So basically, the problem here that led us to have over time calculations for slightly larger integers such as n equals 50 and 100 is we have too many repetitive calculations that give us the same result, and they spend a lot of time. So what can we do? So now we think about storing our results so that we don't have to calculate them repetitively again. And this is when we have dp involved. So we use dpi, so this is an array, dpi to store the fi. So fi is just the ith term of the Fibonacci sequence. So we have dpi equals fi. So what do? We start by having, so every time in dp problems, we firstly set up an original value. So we have dp, so we set up a definition for the array. So what does dpi equals to, right? Or what does dpij equals to? We set up the definition for our array, and then we set up the very original value that helps us to calculate everything else. So in this case, the first two terms are, the original values are dp1 equals 1 because f1 is 1. And also dp2 is equal to 1. So f2 is equal to 1. So these dash lines here are just annotations, so the computer won't read them when they're compiling this program. So basically, this is our definition, and this is our original values. So basically now, we want to figure out how we get from one value to another. So we can say this is our transformation. So, for example, I had DPI, right? So how do I get DPI via calculation? So we start with these two terms, and we know that each term in the sequence is the sum of the first two. So we have DPI is equal to DPI minus 1 plus DPI minus 2. So this is basically the same thing as Fi equals Fi minus 1 plus Fi minus 2. So those two are actually the same concept. So what's the point of this though? Basically, the point here is the reason for DP is we store the value of Fi, so we only compile the function Fi for once. And since, for example, I'm trying to figure out DP5, we know that DP5 is DP4 plus DP3. So actually we start from small to big. So our order is we start from I equals 1 to I equals n. So we start from small to big. And basically here, we say we want n equals 5. We have n equals 5, for example. We start by defining dp3. So dp3 is equal to dp1 plus dp2. And that just gives us 2. And then we have dp4, which is equal to dp3 plus dp2. However, so now we're tempted to run the f function again, the recursive function. However, we already have dp3 and dp2. So we already have dp3 and dp2. dp3 is just 2. We don't have to do anything. We just call the array, and we look at the value when dp3 is here, when I is equal to 3 for dpi. So dp3 is 2, and dp2 is 1. So dp4 is just 3. So now we're gonna figure out dp5. So dp5 is equal to dp4 plus dp3. So we already have dp4 and dp3. No need to call any function. We just plug the values in. We have 3 plus 2, which is 5. So that is way less time consuming than the recursive sequence, because we only need to calculate every function for once, and actually we don't even need to calculate much functions. It's really simply plugging in and adding. It's simple addition. So this is the reason DP is important, and this is also our very first example and the really classic one of dynamic programming. So thanks for watching this video. I hope you enjoy it.